Hello everybody, this is a quick, not really a quick, but fairly short parametrics and vectors video here. So we're going to review concepts in AP Calculus BC for parametric equations and vectors. Okay, so the first thing we have to understand is, okay, let's say we have some function y equals f of x, and imagine that, let's say, we have f of x and x, and we're trying to represent something where a ball is thrown. So this is a physics problem where you have you start at some point here, 0, 0, you throw a ball up in the air and it has parabolic motion, right? And of course it'll go down if you just continue the function. But let's say this was like 4 seconds, and f of x on the interval from 0 to 4. Now, the idea here is, well, in physics, there would be some velocity vector, well, that has, where there's a y vector going that way, and there's some x vector going that way. And of course, at every point we have some x going that way and some y going that way. And this is true for every point. So when you throw a ball in the air, the ball has some velocity horizontally and some velocity vertically, and they're not really exactly affecting each other. So in order to represent each individual component over this interval, to show, like, what's the speed of the x direction of the horizontal direction, what's the speed of the vertical direction, we need to define two different equations in terms of a sum parameter. And so classically, you really, before you have some y equals something x, right, to the something or whatever, something related to a function of x. Now we're going to go here and rewrite two different equations, y of t equals something and x of t equals something. And each of these are going to represent the horizontal and the vertical vectors here. Okay, so they're all connected by some parameter t. So often you're going to get something like y is equal to t squared and x is equal to 2t minus 2. And you're going to have these two parametric equations. These are parametrics, right? Because they're both individual variables, but they're functions, or not really functions, but they're with respect to some parameter. The parameter here is t, and most of the time it will be t. Okay, so now the question I have is, what is dy dt, dx dt, and dy dx? How do we find these three? Well, you might, be pretty kind of surprised at how easy this would be, because dy dt and dx dt are found by straight up taking the derivatives of each of these respective equations. So dy dt would just be the derivative of t squared, which is just 2t, and then dx dt would just be the derivative of x, and that will just be 2. And so there you have the dx dt and the dy dt. Now, how will we get dy dx? Well, notice that we can really write dy dx equal to dy dt over dx dt. Because if you actually finish this out, we notice that the dt's will cancel out to dy dx. So dy dx in this problem is just the derivative of y with respect to t, which is 2t, divided by the derivative of x with respect to t, which is just 2, and dy dx is t. Okay? So this is our final answer. Of course, this would be the answer if they told you that you want to find dy dx in terms of t. Now, this formula right here, you have to memorize. This is something you have to really memorize. And you can really derive this and kind of figure it out on your own, but you have to know that this formula because it's going to be imperative for parametric equations. So what if I took the same, parametrics, and I asked you to find dy dx in terms of x? Well, the first thing we would have to do here is actually we need to somehow have x's in this. So we need to have y equals a function of x. This is what we need to find. So all we're going to do is take the x parametric and we're going to solve for t. So in this case, it'll be t is equal to x plus 2 divided by 2. Now we're going to plug this into our t over here. So therefore, we're going to get y is equal to x plus 2 over 2, all of that squared. Now we can find dy dx very easily, in the sense that dy dx will just be 2 times x plus 2 over 2 to the 2 minus 1. This is just x plus 2, and there you have it. So just very different methods of doing this. Now, in this sense that parametrics is very one of the easier topics here. So just remember this formula circled in red, and there you go. Now the next question you're going to need to ask is, how do I find the second derivative of a parametric? So let's take the same equations. I'm going to write the t a little bit better. And let's find the second derivative. So remember that dy dt is just 2t, dx dt is equal to 2. Okay. From here, we can immediately say find dy dx, because this is just t, as we found earlier. So here's a new formula that you're going to have to memorize. It is going to be the second derivative of y with respect to x is equal to the derivative of dy dx. So you probably expected that, but you need to divide this by dx over dt. Okay, so this is your formula for the second derivative. It's the derivative of the first derivative, and then divided by the x component derivative. Just remember that. So, using this formula, we know that dx is t, and the derivative of t is just 1, and x is just, dx dt is just 2. So the second derivative, in fact, is just 1 over 2, or 0.5. Very easy. So let's say I gave you some new parametrics. I gave you y is equal to sine x, and x is equal to, let's do e to the x. Sorry, what am I doing? Sine of t, sine of 2t, and let's make this a little bit more complicated. Let's say we have x is equal to e to the t squared. Okay? So the problem here would be to find d squared y over dx squared, which just means find the second derivative. Okay? So the first thing you would want to find is dy dx. So label out your derivatives here. So the derivative of y with respect to t is just 2 cosine of 2t using the chain rule. The derivative of x with respect to t is just e to the t squared, chain times the 2t. So now we can find dy dx, which is equal to dy dt all over dx dt, which in this case will just be 2 cosine of 2t all over 2t e to the t squared. And make this a little bit easier for us, we're going to cancel out the 2's, and this is our dy dx. Okay, so now we need to find the second derivative. So let's start out by finding the derivative of just dy dx itself. And this is going to be a little bit annoying, but we need to use the quotient rule here. So the derivative of the top function is going to be negative 2 sine of 2t. And we're just going to multiply that with the bottom, te to the t squared. Subtract derivative of the bottom, we need to use product rule. So we're going to do some big calculations here. I'm actually going to move all of this down. Well, it's okay. So minus, so derivative of the bottom here is going to be e to the t squared plus 2t squared e to the t squared. Hopefully you guys got that. The derivative of the second part is going to be t times the derivative of e to the t squared. And of course, we need to multiply this by oh yeah, that should be fine. There we go. And of course, we just need to multiply that by cosine of 2t and divide all of this by t e to the t squared, all of that squared. Okay, so this is going to be our derivative of our dy dx. Now, from here, we just need to divide all of this, so I'm going to rewrite this. Negative 2 sine 2t e t to the e to t squared minus e to the t squared plus 2t squared e to the t squared times cosine of 2t, all divided by t e to the t squared squared. And we're going to just now, on the denominator, tag in our dx dt, which we know from right here. Didn't mean to erase it. So we're just going to multiply, because the dx dt goes in the denominator. Remember, the second derivative formula is we have a dx dt on the bottom. Okay, so it's going to be e to the t squared, so 2t e to the t squared. And this is our second derivative right here. I had to do a little bit of work. I promise the AP will not get this extreme, but just to show you a pretty extreme case. And that right there, guys, pretty much sums it up for just parametrics in general. So yeah. Now, for vectors. So everything you learned from parametrics, we're going to keep, and you're going to apply those ideas very similarly. So you need to know here that the position vector, denoted by s of t, is equal to the vector with x of t and y of t. So hopefully you begin to see the relationships here between parametrics and vectors. And vectors are denoted like this. So usually something like I, comma j, something like that. Okay, the v signs. Now, don't overcomplicate it. You don't have to worry about what this really means in the AP Calc BC exam. Conceptually, I mean, it's great to know. Vector is something with magnitude and direction. So you might be like, this is a vector. We have this is a vector. This is some vector. Get the idea here. So v of t, which is the derivative of the position vector. So the velocity vector here is just the individual derivatives. Really simple, guys. Really simple. Okay. And of course, the same goes for the acceleration vector. It's just x double prime of t, y double prime of t. And there you have it. Those are the big three things that you're going to need to know for just vectors. Not everything, and don't mistake my words there. This is just how vectors will generally work here, and it's going to be very easy. So there you have it. So if I, for example, gave you that the position vector here, I said was sine of t and ln of t. Well, and I asked you to find v of t, all you would do is just take the individual derivatives. So derivative of sine of t is just cosine of t. Derivative of the natural log of t is just 1 over t. And there you would have it, guys. This is all you need to really understand about how to take derivatives of vector functions. Now, of course, we could always go backwards. So let's say I gave you v sub t is equal to cosine of t and e and 2 to the t as an example. And I gave you that the initial conditions are x of 0 is equal to 0 and y sub let's say y sub 1 is equal to 2 as our initial conditions. So you would do s of t and you would integrate like you normally would, and you would have, but remember, x of t is equal to integral of cosine of t dt, which is just sine of t plus c. Now we use the conditions. We know 0 is equal to sine of 0 plus c, so that means c is equal to 0. So our x of t function itself is just sine of t. So we're going to write that here. Now for our y function, well, the integral, so y of t is equal to the integral of 2 to the t dt. Now, of course, this is just the same as 2 to the t divided by ln of 2 plus c. We know that 2 is equal to 2 over ln of 2 plus c. C is equal to 2 minus 2 over ln of 2. So our y of t function is just going to be 2 to the t ln of 2, that's poorly written, plus 2 minus 2 over ln of 2. So our y of t function is going to be 2 over ln of t, 2 to the t of course, plus 2 minus 2 over ln of 2. And there is our position vector. There you have it. So that's another type of question where you're going to be given a velocity or an acceleration vector and going to have to integrate. And if I'm most likely sure they will give you an initial condition, otherwise you just put plus c. Of course, along with parametrics, you're going to have to understand when the particle is decreasing, increasing, and there's another concept here that we have to understand, and that is speed. And speed is the absolute value of velocity, and in vectors, this is really the magnitude. And so, for example, let's say I have some vector here, x comma y. The magnitude of this vector, and let's say this vector is v. The magnitude of v is equal to the square root of x squared plus y squared. Okay, so let's say I gave you a velocity vector, and this is equal to e to the t, comma, I don't know, 2t. So our velocity, our speed will just be denoted by the square root of e to the t squared plus 2 to the t squared. Very simple. And so let's say I wanted to say find the speed of particle at t is equal 0. Well, just plug in 0 here. You're going to get e to the 0 is 1, 1 squared is 1, so square root of 1 plus 0. So this is just going to be 1, and so that's the speed of the particle right there. Okay, so just understand that in vectors, when they ask for speed and magnitude, it's really asking for the magnitude of the vector. So this is another key concept that you have to understand here. Okay. course, we also have the arc length formula. So this is our kind of last little topic here, and that's the arc length. Okay, so using vectors on some vector valued function, well, we can find the arc length denoted as L is equal to the integral from a to b of the square root of dx dt squared plus dy dt squared with respect to t. So this is the length of a parametric curve. Okay, so, and you might recall that the length of an arc was actually this formula. You might have remembered it. Should, to review. And so if we simply change everything here a little bit, so remember that, and this is really a proof for how we got to this formula, so just enjoy the proof, I guess. Remember that dy dx is dy dt over dx dt. So we're going to say this is equal to the integral from a to b, the square root of 1 plus dy dt squared over dx dt squared dx. Pretty much, and what you're going to notice is that from here, you're going to be able to arrive at that original formula. I'm not really going to get into that because I want to get into a problem here, but this is how you would approach a proof, and I hope you guys see where this is going here, where we could rewrite this in some form. Okay, so this is pretty much all you need to know. Oopsies, recording got a little cut off there, but that's pretty much all you need to know here, guys, to find this arc length formula. And so a real question here is, let's say I gave you the parametric equations as follows. And I asked you find the length of the curve on the interval from 0 to 1. Well, first thing I would do is find dy dt, and this is going to be e to the t. Dx dt will just be 2t. And remember that the length is just the integral from on the interval. And of course we have the square root of e to the t squared, all of this squared, plus 2t squared with respect to t. And you're going to do this on your calculator, of course, because I simply do not think that is even remotely fun to integrate. So let's just do that real quick. E to the plus 4 dx, and you should get something close to 2.009748612 as your big decimal number here. And there you have it, guys. So this is pretty much all you need to know for parametric. So I'll go for everything here. So just understand that a parametric represents a function in terms of some other parameter. So to a y and an x function or an equation, they're not always going to be functions. Parametric curves are not always functions. Actually, just really remember that. I made a slight misinterpretation. Not always functions. Okay, they're just parametric curves. Well, we can find the rate of change of these curves by taking the individual respective derivatives of y of t and x of t, and we can use this formula to find the dy dx, how it moves along the plane, not just individually in their own respective components. We can solve for y in terms of x by solving for t in the x equation and just plugging whatever you get for that. We can take the second derivative with the formula highlighted here, and it's really just the derivative of dy dx divided by dx dt. And so there you have it. Here's an example problem that we did. And then we have vectors, which are adding on to parametric, so we're building a little bit here. The position vector is just represented as a coordinate vector of x of t and y of t. The derivative is just the individual derivatives as a coordinate, and the same goes for acceleration. You can be given problems here where you're given the velocity vector, right, as we see right here. But we're going to have to find the position vector, and we're given some initial conditions. And so you can kind of see how particle motion FRQs are really going to be key here. And of course, the speed of the vector is just the magnitude, or sorry, the speed of the particle is the magnitude, and the magnitude for a vector is given by this formula. And of course, we have our arc length for parametric curves, which is a little bit different from the arc length formula you knew back when you learned things like logistics and Euler's formula and all that stuff, early days of Calc BC. Now we have a new formula here that you're going to have to really memorize. Not too hard to memorize. You could actually derive it as with the setup I gave you here. And here's an example problem. And there you have it, guys. This is all you're going to really need to know for parametrics and vectors for Calculus BC. Stay tuned for a polar video coming up, and have a great rest of your day.